Welcome back to BAS 120. We're going to go through the examples in Chapter 6. So we're going to start with example 6.1, where it just gives us sampling plan and some examples. So the objective would be we might want to estimate the proportion of golfers that subscribe. Then we'd do a target market. We might target golfers over 25. Population frame would be the list of golfers who purchased equipment. Our operational procedure might be that we're going to email people. Statistical tools might be pivot tables in Excel. All this is an example of a sampling plan. Example 6.2 is how to do some random sampling. So what we've done here is we've taken the sales transactions, and all I've done here in these cells is to get a random sample. I went to data analysis, came down here to sampling. You can see here I hit random, give me 5 random numbers from this field. I highlighted the field, and then I just told them where I wanted to put it. So up here you give it the input range. Column at the left needs to be numeric. What sampling method? Do you want to be random or periodic? I wanted it random. Number of samples, I asked for 5. You could ask for more. Where do you want to put it? I put it up top. So there those are. And then I just did the same thing, only here we ask it for a periodic sample. So that allows you to go into a large database and do some random or periodic sample so you can set up your experiments. Here's a sampling experiment. It's in the book where they talked about, hey, let's have a uniform distribution from 0 to 10 numbers. Now remember, our expected value formula for that would be half of the range, and the variance would be 1/12 of the difference squared. I've put them into a little equation here. Now, to get these observations, the book goes through different numbers. I did 5 observations, 4 samples. All I had to do is I just said, give me a random number. And remember, Excel is going to generate a random number from 0 to 1. Then if I want random numbers from 0 to 10, I just multiply by 10. That's how I got those. I then took an average mean by saying, give me the average of those numbers. The way Excel works, when I click this, it updates my random numbers. This gives me my overall average. Now, the whole point of this book, and I didn't do 20 of these, but the whole point here is as our sample size increases, our sample means are always going to hover around 5. But look what's happening to our sample standard deviations. They're going down, down. They're shrinking. So the power of large samples is they drive your standard deviation of the sample means goes down. All right. Another problem. Then they ask us, how can we take the empirical rule? So the empirical rule, you have a couple of choices. You can say, I want 99.7% accuracy, or I want 95% accuracy. This would be 3 standard deviations away. This would be 2 standard deviations away. So the empirical rule is 2 standard deviations to the right or left of the mean covers 95% of our data. 3 standard deviations covers 99.7. So I've given you a choice here. I said let's be 3 standard deviations, but you basically could change it. How accurate do you want to be? The orange are calculated based on what we set up here. So it's going to be 3 standard deviations to the left or right. Here it tells us the different sample sizes, tells us the sample mean, and it tells us the sample standard deviation that we arrived at. Now this cell right here is going to calculate that range. It's going to calculate the range by just saying the high end of the range is going to be my sample mean plus 3 times whatever my standard deviation is. My low end of the range is going to be the mean minus 3 times the standard deviation. And then I added in here the total range, which is just the difference between the high and the low. Now, as you would probably expect, as our sample size increases, our range of our high to low, where we're 99.7% confident the numbers will fall in that range, shrinks from close to 5 down to basically a half because we've increased the sample size. Very powerful. As you do sampling, as you increase the sampling size, you are going to reduce the amount of sampling error that you have. Example 6.5 talks about computing the sampling error of the mean. Remember, our formula for the sampling error of the mean, if you've gone through the previous videos, is the standard deviation divided by the square root of n. This is in situations where we know the standard deviation of the population. So that's what we're assuming here. We know the standard deviation of the population. So once again, our sample size, our sample mean was 5, our sample variance, our sample deviation, and there's our sample error of the mean, which is just this equation right here. And you notice the same stuff going on. As our sample size increases, our standard error around the mean decreases, and our high and low range decreases also. Example 6.6 was all about the probability, using probability to calculation. So, probability of one customer purchasing more than $40. If we know the mean is 36 and we know the population standard deviation is 8, what is the probability that one customer comes in and purchases more than $40? Well, the probability of that is we can just simply use our tools. Now, normal distribution, norm dist, is going to tell us the population from 1 to left. But we want to know how much more. So we're going to take 1 minus whatever that probability is. So 1 minus norm disk. Let me demonstrate the norm disk function. We say norm. Let's look them up. Let's go to statistics. Let's look up our norm disk. Norm disk, okay. Now, our X in this case is we want to know people 40. Our mean is 36. You can either punch it in or I have it do these cells so you can change it. Our standard deviation is that, and we want it cumulative, so we want it true. Now remember, this is going to give us the probability from left to right, so that basically gave us the probability of less than 40. So if we say equals 1 minus this, we get our 0.0385, the probability greater than 40 of getting 1. Now, what's the probability that we get a sample of 16 and that average of that 16 sample population is over 40? Well, here we have the sample size we're assuming, the mean and the population again. There's our X value. The standard deviation of the sample, remember our formula, is going to be our population standard deviation divided by the square root of our sample size. So our sample size here is 16. So that takes the standard deviation of the sample down to 2. Now we just do the same norm disk equation, only our standard deviation has changed. Well, since our standard deviation has shrunk, now the probability, we're up here, the probability of getting one person purchasing over 40 was was over 30%. Look what happens. The probability of getting a sample size of 16 that are over $40 of spending is down around 2%. So sample size is very powerful in our ability to bring meaning to the probability and the statistics. All right, now they talk about calculating a confidence interval. So a confidence interval is how the range in which we feel within a certain percentage that the population will fall in. So we might say 95% confident it falls in this range, or 99% confident. So here we've inputted our alpha, basically how accurate do we want to be. It tells us the standard deviation of the population. It tells us the sample size. It tells us the sample mean. So the results, our confidence interval is just 1 minus our alpha. Our standard error is just our standard deviation of the population divided by the square root of our sample size. So once again, our standard error is going to shrink as our sample size goes up. Our error, remember, is going to be our z-score times our standard error, which you can use a confidence.norm tool within Excel that'll calculate that error. Then it's simply taking our mean plus our error for the upper limit and our mean minus our error for our lower limit. Now, the only trouble with all of that is most of the time you don't know the standard deviation of the population. So in those cases when you don't know, what we're going to do is use a t-distribution, and instead of using the standard deviation of the population that we don't know, we're going to substitute the sample standard deviation. So we have our alpha again. We have our standard deviation of a sample, which we're going to assume is we're going to assume, because we don't know the standard deviation of population, we're going to use the standard deviation of the sample. But that's going to add a degree of freedom, which we're going to talk about here in a bit. There's our sample size. There's our sample mean. Our confidence interval, once again, is 1 minus the alpha. Our standard error, once again, is our standard deviation of the sample divided by the square root. Now, we have degrees of freedom, which is our sample size minus 1. And then our error, we can use, instead of a confidence norm, we use a confidence t, which gives us where that error is. Once we have that, same as the other one, we just do our upper limit is the mean plus the error. The lower limit is the mean minus the error. Now, we've covered it for when we have a normal distribution. When we don't know the standard deviation of the population, we use a t-distribution. But what about when we have a proportion, like foul shots or win-losses, success-failure? Well, we're going to do it somewhat similar. We're going to look at our alpha. We're going to look at our sample proportion. What percent of the time are we successful? In this case, 25% of the time. Our sample size is 24. Our confidence intervals, once again, 1 minus the alpha. Our standard error is a little bit different. We take the square root of our sample proportion times 1 minus our sample proportion, often called p hat, our sample proportion, divided by the sample size n. We calculate a z-score by going to norm INV, and we trick it a little bit. We say what is our probability, and we say if we have a distribution of a mean of 0 and a standard deviation of 1. Then it's the same routine. We take our mean plus that z-score times our standard error, and the lower limit would be our mean minus the z-score times the standard error. Now, what conclusions can we draw? Now, so when we talk about if we have a mean of 800 and we get a sample mean of 796, can we conclude anything? Well, with an alpha of 5 and a confidence of 0.05 and a confidence interval of 95%, the 800 is within our range of 790 to 801. So we would conclude that we have not disproved that the population mean is different from 800. So the way we'd calculate that is we've assumption our alpha is 0.05. Standard deviation of the population, we're told, is 15. Sample size 25. Sample mean 796. We'd calculate our confidence interval the same way. Our standard error would be the standard deviation divided by the square root of the sample size. Our error would be we'd do confidence norm again, and we'd look at our upper range and lower range, and then we'd say since 800 is within that range, we would not reject that 800 is not the mean. The next example, 6.12, talks about elections. How can we figure out whether a candidate's going to win an election? Let's say we poll 1,300 people. They respond 692, say they're supporting our candidate. We just calculated that proportion. 692 divided by 13 is 53%. We want to be 95% confident, so we picked an alpha of 0.05. There's our confidence interval. There's our standard error. There's our z-score once again. There's our upper limit. There's our lower limit. Now, to win the election, you got to get 50% or more. We're 95% confident that it'll range between 0.05, 0.505, and 0.5594. So we can conclude we're 95% confident based on this exit poll that we're going to win the election. Last piece is predicting intervals. So this is when we're using a t-distribution, and we're going to come down here and calculate our t-score. We're going to calculate our standard error. We're going to calculate that error. We're going to calculate an upper limit and a lower limit. The last thing I want to touch on is example 6.14, where we talk about sample size. So this is kind of reversing the logic, not are we 95% confidence in an interval. We're going to say, what sample size do we need if we want an alpha of 0.05 or a 95% confidence interval? We have this standard deviation, this mean, and we want to be plus or minus 3. We want to have a range of plus or minus 3. So what we do is we come up here and we do our norm is, we find our z-score with the norm I and v, and we calculate per the equation. We've just used algebra to solve for our sample size for n, which you've got right there, and then I just rounded this up, used a round up function within Excel to take whatever we calculated here and say, well, you're going to need that 97th person. So that's how you can sort of reverse engineer with the equation what your sample size needs to be. So there's about 14 examples that we've gone through on this chapter on how to do sampling. Any questions, let me know.